Okay, so hi everyone. Thank you for inviting me here to talk to you today about how we have contributed to the AQUA-FAANG project at Select. So my name's Rachel, and I'm the manager of the lab at Select. So before I start, I just want to make some acknowledgements to some of the team that were heavily involved in the project, some of which are here today. So we have Stelios and Max, who are in our analytical team, and they worked a lot on the bioinformatics side of the panel development. And then we also have Paolo, Pauline, and Akis, who were involved in a lot of the practical side in the lab. So for those who might not know who we are, Select is a spin-out company from the University of St Andrews in Scotland. It was founded by Professor Ian Johnson and Tom Ashton, and we are still based in St Andrews. What we do is we are a specialist genetics company for aquaculture, fish farms companies. So we provide broodstock management for genetic improvement, some consultancy services and other lab-based services as well. And yeah, we celebrated our 10-year anniversary this year, so it's very, very exciting for us. So the majority of the work that we do in the company is breeding program management for our long-term customers. So these range from smaller producers to some of the global leading players in aquaculture. So we're slightly different from the AQUA-FAANG project in that we have customers all over the world, not just in Europe, and we work with a diverse array of species as well. So from finfish to shellfish and bivalves as well. And what we do, we carry out various selection methods to help improve their genetic breeding programs, depending on the goals of the customer, obviously, and what their economic priorities are. So that can be from classical pedigree-based selection, just for managing inbreeding control, or if they're interested in specific functional markers, we can use marker-assisted selections. And then we can also provide genomic selection to improve those accuracies on specific traits. So from a lab point of view, one of the biggest challenges for us is choosing the type of technology that we can use for all of our customers. It has to be suitable for everything that they need. So really the big challenge for us is balancing not only the internal costs, sorry, don't know what's happening, balancing those internal costs in the lab, but also the financial appetite of our customers and whether they want to really invest in genetics alongside their productions. We also need to consider the practical implications because we like to do everything in-house, and also have the ability to tailor our lab processes to our customers' needs. So yeah, there's a lot of big players out there offering very similar services and equipment. And yeah, basically we had to choose the best one for us. We used to use the Fluidigm, but that started to become a lot more expensive. So we have decided to implement amplicon sequencing panels into our breeding programs. So this is based on Illumina technologies. This was the best solution for us overall. And the reason being is that we can actually design our SNP panels in-house, and we can tailor that for our customers. So we don't have to rely on specialized kits from the suppliers. We can develop everything ourselves at relatively low costs, and this means we also don't have to rely on external providers. So we can do everything in our lab, and we have basically the control of the entire process from getting the samples to creating the data, and also the turnaround as well, depending on the priorities of our customers' breeding programs. And the nice thing about the Illumina-based technologies is the integration of new markers, and that's kind of how we fit in with the AQUA-FAANG project, because again, we can do that quite easily at low cost compared to those high-density chip-based platforms where you really need to commit to high sample volumes to get that cost down. So in our lab, we developed these amplicon sequencing panels, and it's a multiplex PCR approach. So effectively, this is our workflow. So when we're developing a panel, we will select some suitable SNPs to go in the panel. We will design the primers, and then we will test all of those SNPs in combination through a series of PCR steps. The first PCR is amplifying that SNP amplicon, and then the second PCR is adding on the adapters and indexes so that we can demultiplex later after the sequencing reaction. Then the data will go through our in-house bioinformatics pipelines. We will then analyze the data, look at the coverage across all of the SNPs, how do those primers interact with each other, and then we can go back and either remove SNPs that don't work or re-optimize those loadings to then create a panel that is suitable for routine genotyping. So once we're happy with our panel, we'll then build the genotypes, and that data is then passed on to our project managers, who are the guys that do all the analysis in-house, the pedigree reconstructions, and mating plans for our customers. And just to say that our panels range from about 100 to 400 SNPs, depending on if they're using pedigree-based selection or genomic selection with imputation. So the advantages of the Illumina-based platform and amplicon sequencing is that it really fits in with the goals of the AQUA-FAANG consortium in being able to develop these experimental tools that we can use to understand functional variation in European aquaculture species in this case, to ultimately improve selection and achieve that genetic gain. So in this project, we were able to develop functionally enriched panels quite fairly easily in the lab, which can now be used for either parentage assignment or genomic prediction. And again, it was much more cost effective to do it this way than it was to invest in those high density chip-based platforms. And now these panels can be effectively used as a proof of concept moving forward. This is just to describe the two panels that we developed. So we developed a low density panel enriched with functional markers for two species. The first one, European sea bass. So back in 2021, we received around 30,000 SNP positions from Carolina and Ross. And from that information, we used some public resources from 2B RAD sequencing and whole genome sequencing to basically select a number of SNPs for initial design for the low density panel. So in this case, we had to split our primers into two separate pools based on the interactions during the optimization process. And after 3 optimizations, we managed to develop a base panel of around 348 SNPs distributed across the genome in bass. And then in 2023, as we've all heard about, the really exciting discovery by Robert's group, they found a major QTL for VNN resistance in sea bass. And the nice thing about, again, the amplicon sequencing panels is we were able to take that base panel that we developed 2 years ago and easily integrate some of those markers into the panel. So in this case, it took around three optimization runs, and now we have a final low-density panel of around 367 SNPs. So there was some dropouts, but ultimately we were able to keep the key SNPs in there, the functional markers. And when we do optimize our panels, we'll always look to see if there's any additional markers in the literature that we could integrate that could be used in future breeding programs for validation. So when we integrated the SNPs into our base panel, we were just curious to see how they performed in some of our historical populations or samples that we have at Select. So we were just looking at the genotype frequencies. Here's just some 6 different functional markers that we added. And as Robert said, the homozygous recessive genotype confers resistance to VNN or explains a higher variation in resistance. And while some SNPs are not very informative, we can see for 3 of them that there's, population 4 seems to be missing that homozygous recessive genotype. So there is potential for marker-assisted selection with these SNPs moving forward. But obviously this is all very exploratory data. So the next panel was for gilt-head sea bream. It was the same process. So again, we were given some SNP positions that we filtered using some public resources and selected about 353 SNPs for initial design. In this case, we were actually able to optimize the panel using a single primer pool, so it was much easier to work with. And after 2 optimization runs, we now have a base panel of 301 SNPs, again distributed across the genome of bream. And in 2023, we were provided some functional markers for resistance to photobacteriosis, again, which we were able to include in our base panel that we created 2 years ago fairly straightforwardly in 2 optimization runs. So our final low-density panel for bream contains 311 loci because we were actually able to develop a haplotype from some of those markers. So yeah, and then we did the same in this case with some of our historical samples just to see how they perform. And this time we knew what the favorable alleles were. And in this case, for the SNP 1189, we can see that the population 2, 25% of the population have the homozygous alternate genotype, so are possibly more resilient to photobacteriosis. And the same with the SNP 381, where most of the populations have the favorable allele in the population. So just to end, we are also offering high-density SNP panels for genomic selection. So as Christina showed in her research, from about 5,000 SNPs onwards, we don't really see a huge improvement in accuracy across different traits. So we were able to find a way to be able to offer high-density genotyping using the same sequencing-based method, but this time instead of PCR, multiplex PCR, it's a probe-based method, so it's more targeted, and we get a more even coverage across the loci. And this also means that we're able to continue our breeding programs that have been using our original sequencing panels as well, because we can cross-platform move those samples. And again, it's flexible, so we can adjust the panel over time as well. And yeah, it should be good for our customers moving forward. So that's it. Thank you for listening. If anyone's got any questions, there's quite a few of us here today from Select, so I'm sure we'll be around to answer any questions. Thank you.